Class. Hmm?
Hi everyone. So we'll wait for a couple of minutes, and then we can start.
Sir,
Yes.
sir, meanwhile, can you tell us about how you're planning to conduct the exam? Like, we
Sure.
got a schedule and yeah.
Yeah, sure. Just give me one second. Yeah, so you have already submitted the solutions of one assignment, and I've given you another assignment. So those will be two evaluation components, and in the midsem exam there will be some questions. So the midsem exam will be an online test, and it will have some questions which you can complete in 3 hours. So it will be, I don't know how many questions, but it will be some formulation type of type of questions, which are much simpler than the ones you got in the assignment, because you have a time limit. So you can take that test anytime, at any time of your convenience, at 3 hour in a 3 hour window. So that will be the format, and I think you can submit both. You can submit your answer both in a Word document, or in, you can write on pen and paper, and then you can scan the image and upload, similar to how you are submitting the assignment.
So, sir, like on 5th, we'll have a 3 hour window, like throughout it. So, exam will be online for 24 hours, and in which we have to choose some 3 hours where we are comfortable.
Yeah. It will not be 24 hours. It will be more than that. Maybe 3, 4. I'll keep a window of 3, 4 days or whatever, and you can take it on any day of your convenience. But yeah, once you start, you have to submit within 3 hours.
Okay, sir. Answer questions will be kind of the questions like easier versions, but the taste would be similar as what we are doing in assignments right now.
Yes, exactly. And so in the assignment you got a full problem to solve. So in this in the test, there might be a few questions which will be just how just on a single constraint. So how will you formulate a particular rule? So that type of questions also will be there.
Okay, sir. And sir, one last question. Like in assignments, at some can we get a review on our assignments, or like before the midterms, so that we know exactly how to write? Because yeah,
Okay.
because I don't
Yeah, or like a
yeah. So
demo
like if
solution for the first one.
yeah,
Sure. So for the first assignment, we went through some of the all the submissions that people did, and but yeah, I didn't have a demo solution as such. But yeah, for the second assignment, we can discuss that in the next class. Probably that's a good idea. So I can discuss the demo solution of the second assignment in the next lecture. And probably I'll put up something for the first lecture also, demo solution, based on whatever all of you submitted is everyone has there was some plus, something's correct, something's wrong in all of your solutions. So I'll put that together and I'll put up, we can discuss the demo solution in the next lecture.
Thanks a lot.
You mean for the assignment one, right?
Yeah, I meant for the assignment one only. So right now I've given the second assignment on the optimally refilling ATMs. So on that, and so in the next class, what we'll do is we'll first go through but next class, but the problem is for the next class, the submission deadline is 2nd March, right? So if you can, is it possible for all of you to submit by Wednesday? Not by Wednesday, maybe by Tuesday. Then I'll get. So basically, I was thinking of taking your last class before midsem on Thursday. Then if you submit by Tuesday end of day, then I can go through that on Wednesday, and then Thursday we can discuss those assignments. Is that possible to submit by Tuesday, or it's too early?
Sir, like
It's a very short window.
Mm-hmm.
If you can do that for assignment one, it would be very good for me
Sure,
because
sure.
I already have it.
Right. Correct.
We can try.
I'm sorry. Hello.
Yes, sir.
Sorry, there is some network issue. I'm not sure. Can you speak
Hello.
again? Yeah, I can. Hello. Can you hear me?
Yeah.
Okay. Yeah. Sorry. Can you come again?
Yeah. Hear you.
Let me stop my video one
No,
second.
sir. All the doubts are clear.
Okay, all that also. Yeah, so what I'll do is in the next class on Thursday, we can go through a demo solution of the first assignment, the sports match scheduling. So that will give you some idea. I think it's basically it'll basically be a collection of the correct things from the different assignments. So I'll put that in one document and we can share. And the assignment that you're doing currently, the second one, you can submit me the solution by 2nd of March, as I mentioned earlier, and then we can probably in the once after your midsem we can discuss the model solution for that. Okay. Any other questions? Okay. So Thursday.
Sir,
Mhm.
I have a question for the second assignment.
Yeah. You had a question on dynamic models. So first of all,
Yeah.
I didn't understand what is dynamic model.
So, so we have like a 1 week window, and we are
Mhm.
like assigning like vehicles and like amount to go to ATMs. So
Mhm.
if let's say like something happens on third or fourth day, and like something that we did not anticipate, and something happened, and that
Uh-huh.
is like a hard constraint. So,
Mhm.
like, can I like change? At the start of the week, we are like assigning things, but if something happens in like third or fourth week and we have to like do it, so what to do?
Yeah, so that's a good question. So if once you have planned, let's say for 1 week, and something unanticipated happens on the third or fourth, then obviously you cannot do anything about it. The only so the then the in reality also that happens. So that's not a very imaginary scenario. In reality, definitely happens rather. So in that case, the people, the people who are the operational people, they will try to circumvent the problem and find some manual solution to that. So for example, let's say a vehicle breaks down and you have allocated the vehicle. So obviously we cannot, we still need to refill the ATM. So in that case, probably the ATMs, probably the vehicles another vehicle will be assigned only for, in this example, another vehicle will be assigned only for as a substitute of that vehicle. That is one solution. Or let's say this vehicle which broke down, that was supposed to refill let's say 20 ATMs. So we can spread those 20 ATMs over let's say 5 different vehicles which are on a similar route, which are serving ATMs, nearby ATMs. So that will be the solution. So you really can't do anything about this. The other thing that you can do is the operations people can do is they can rerun the model. So once so let's say, again, if in the middle of the day the vehicle breaks down, then you really can't do anything about it. But you can reallocate those ATMs to other vehicles. So for that you need to rerun the model again. So you need to take that vehicle out of your set, and you need to rerun the model. So either the model will allocate a different vehicle, or it might spread those ATMs of that vehicle over other vehicles. That would be another approach.
Okay, sir.
Yeah. Okay. So any other question on the second assignment?
Excuse me, sir.
Yeah. Yes, Ayush.
Not on the assignment, but could you upload the recordings of the offline class that you took last week?
Okay, sure, I'll do that. Yeah. Okay. Okay. Any other question on the assignment or anything else? Okay. So one question I had is, ideally, I was supposed to take a class on Monday, but Monday, Tuesday, Wednesday, I would be busy with some other work. So I was planning to take a class on Thursday instead of Monday. So, and that would be the last class of this, last class before mid-sem. So when is a good time? So I have your calendar with me, schedule with me. So Thursday, next week, Thursday, 27th, which is a good slot? I see that.
For me, on Thursday, I am free only after 3:30.
Okay, that means including 3:30?
Yes.
Okay. Mhm.
So we have IMF classes only on weekends now, so that slot is free.
Oh, so 3:30 is free for everyone?
Yeah.
Okay, fine. So then Thursday, we'll do 3:30 then. Okay, fine. So the next class after today will be 3:30. Thursday, 3:30.
So we won't have a Monday class, we'll just have a Thursday class coming week.
Yeah, right. So so this current one is lecture 15. So that's next week, Thursday is 3:30 class will be lecture 16. And after that, you will have I think your mid-sem exam is the following week, right? 3 to 8 probably. And then again, we'll resume on that week of 10th. Okay. Fine. Okay, so fine. So let's start with today's lecture then. So what I have today is we'll go through few topics. So let's see how much we can do. Sharing my screen, right? Okay, so what we'll do first is, are all of you able to see the presentation?
Yeah.
Okay. So airlines is another major area where we use operations research. And so in this, the first half of today's lecture, we'll go through few cases or applications of OR in airlines. And this is mainly related to flight assignment, aircraft assignment, scheduling, those kind of problems. We'll not go through. Another big area where optimization is used is revenue management, but we'll not go through that in today's lecture. We'll go through that in a future lecture. So this, what you see in this this screen, this slide is the different types of problems that exist in airlines. So we start from a strategic level planning and we go down to operational level planning. So the first decision that we need to take is so in India, like we have a lot of airports, and whenever I mean earlier we used to have only airports at major cities, but right now you have airports at probably 50 plus cities. And when an airlines decides now the decision an airlines needs to take is whether it should be serving a particular airport or not. So for that it needs to look at how many passengers at the passenger forecast for next 3 years, and how much would be the revenue and the cost versus the cost factor when if it decides to operate flights to that particular airport. So it's again a mix of both machine learning and OR. So looking at these factors, the airlines decides whether it should be serving an airport or not, and also it needs to look at how many aircraft it has and uh, how much it expects to grow to. Meaning, so let's say Indigo is the biggest carrier today in Indian airline industry. Probably, I think 60% market share is of Indigo. So they can, and they have a lot of aircrafts at their stake, so they can operate flights to every airport. But smaller airlines like, let's say, SpiceJet, which don't have that many flights, they cannot operate. They cannot afford to operate flights to every small airport. They need to probably look at only the bigger airports. Or again, it depends on the strategy of that particular airline. Some airlines might want to operate in only, let's say, particular zone of the country. Some airports might want to some airlines might want to target only airports in tier 1 and tier 2 cities, etc. So that is the first step in planning. The second step is deciding the size and composition of the fleet of the airline. Meaning, once the airlines decides that it would need to serve a particular airport, it needs to decide how many aircrafts it should it should have in the next 3 years, and what should be the size of the aircraft. So whether it should go for 10 big aircrafts and 20 small aircrafts, or 20 big aircrafts and 10 small aircrafts. So those kind of decisions. So because accordingly it needs to order the aircraft from the aircraft manufacturers. And today there are only two globally. There are only two aircraft manufacturers. One is Boeing and the other one is Airbus. And and obviously they don't they will it's not a they don't have stock of aircraft. So they will start manufacturing the aircrafts only once they receive the order from airlines, because it's very customized, and secondly it is the cost is very high, and the lead time of manufacture is also very high. So the aircraft manufacturers also need sufficient lead time to manufacture the particular size and type of aircraft that the airlines is looking for. The third step is finding when and how often should each leg flight be operated. Meaning that, let's say I decide that I need to operate. So let's say today I don't have any flight for let's say Nagpur, and I decide to start flights to Nagpur from, let's say, Delhi, Mumbai, and Kolkata. Then I need to decide how many flights I should have in a day, how many Delhi to Nagpur flights I should have in a day, or Mumbai to Nagpur, and what should be and first of all, whether it should be daily, or whether it should be only few days in a week, or it should be on weekends. Those kind of decisions. And if I have multiple flights in a day, then what should be whether it should be one flight in a day or two flights in a day, and should it be a morning flight or evening flight. So those kind of decisions. The next one is, once we decide the flight leg, then we need to assign the aircraft type to each flight leg. Meaning meaning if it's a smaller airport where you do not expect that many passengers to fly, you can probably allocate a smaller aircraft, or you can have multiple flights in a day with a smaller aircraft, or you can have one flight in a day with a larger aircraft. So those decisions need to be taken. So for example, if it's a Bangalore to Tirupati flight, then it's just 300 kilometers, so probably not many people will be using it. So they would probably assign a smaller aircraft. The next stage is designing the sequence or deciding the sequence of flight legs each aircraft will have to operate. So this is what we already discussed earlier. So once we know what are the flights, what are the timings, and I know what is my how many aircrafts I have, I need to decide which aircraft will be following which will be taking which route. So I might decide, the model might decide that I'll have a aircraft flying from Delhi to Mumbai, Mumbai to Trivandrum, Trivandrum to Chennai, Chennai to Kolkata, Kolkata to Nagpur, Nagpur to Delhi. So at the end of the day, it should return to its base location. That is Delhi in this case. So that is the next stage, and after that is we also design the work schedule for each crew member. So every flight will have certain aircraft crew. So we need to assign. Now, while an aircraft doesn't have any working restriction on the number of working hours, um, it can fly for 24 hours, but obviously the aircraft crew will have a limitation on the number of working hours. So let's say it's 12. So we need to assign the aircraft crew in such a manner that they return to their base location at the end of the day, and whether the aircraft crew will be staying in the same aircraft or they'll be moving to a different aircraft, which takes them to their base location at the end of the day. Those decisions need to be taken by the model. Okay. So any questions on this? Okay. So next, so the first case study we'll go through is flight schedule allocation for hub airports. So before I go into the slides, so what it means is you have seen that we have already discussed about the hub and spoke concept in an earlier lecture. So there are certain airports which are like hub airports, meaning they are bigger airports, and you will have connecting flights from smaller airports. So those will be spokes. So for example, in an Indian context, you might have a flight from let's say Jaipur to Delhi. I mean, let's say there's a passenger who wants to go from Jaipur to Mangalore. So there may not be a direct flight from Jaipur to Mangalore because these are much smaller airports. So there might be a flight so the passenger might need to take a flight from Jaipur to Delhi, Delhi to Bangalore, Bangalore to Mangalore. So in this case, the hub airports are Delhi and Bangalore, and the spoke airports are Jaipur and Mangalore. So what this model will essentially do is there might be, and again, all the passengers who are in the Jaipur to Delhi flight, all of them will not be going to Bangalore or Mangalore. So some of them one passenger might be going to, let's say, Gwalior, one passenger might be going to Guwahati, and so on. So how do we ensure that, and there will be different flights for Delhi to Guwahati or Delhi to, let's say, Indore, and so on. So how do we ensure that the Jaipur to Delhi flight is connected to the maximum number of has the maximum number of downstream connections? So the passenger sitting on Jaipur to Delhi flight doesn't have to wait for a long time for the next flight. They can quickly change their flight and move to reach their final destination at the earliest. So that is what this model tries to solve. And again, the connecting time should not be too much. Sorry, not the connecting time. The waiting time at Delhi airport should not be too much, or it should not be so less that the passenger cannot switch the flight within that short period of time, right? So that's what the model strives to do. So this is what I have mentioned here. So in this case, so there can be two kinds of transfers at an airport. So let's say at Delhi airport, there can be two kinds of transfers. One is coordinated transfers, that is those planned by the airlines for the passengers, meaning when you try to book a flight from your origin to destination city, you get some direct flight options, you get some non-direct flight options, especially if it's if either your origin or destination is not a tier 1 or tier 2 city. You will generally not get a direct non-stop option. You'll get a one-stop or two-stop option. So those are what we call as coordinated transfers. So those are planned by the airlines. On the other hand, we might have self-help transfer also, which means the passenger might need to create that itinerary for the set of the first leg, second leg, third leg, so on, to reach the destination. Meaning, if it's so, for the example I gave earlier, the passenger might need to book three different flights. Three flights separately: Jaipur to Delhi, Delhi to Bangalore, Bangalore to Mangalore. So they might need to do three different bookings. So for both of these kinds of transfers, this model can be used. And how do we quantify? So what we try to do is we try to maximize the number of transfer opportunities, that is the number of feasible flight connections. And what are feasible flight connections? Those that are competitive, operationally feasible. Competitive meaning the price is not too high, because generally the rule is, as you increase, the number of more the number of flights that you need to take, more will be the cost in general. It's operationally feasible. That means connecting time is not too low or too high, and it's convenient. And the passengers' waiting time at the hub airport is reduced. So that is the objective, and feasible. And we try to make sure that we maximize the number of feasible flight connections. So feasible flight connections are those that meet the constraints of detour time and connecting time. So first, let me go to connecting time. So connecting time is what we discussed earlier. So it is the time difference between the arrival of a flight at the particular airport and departure of the flight to the next destination at the same airport. It cannot be less than a certain minimum connecting time, because the passengers would need certain minimum time to change the flight to move from for domestic transfer or international transfer, and also some time would be required by the airport, or the airlines, to transfer the baggage to the second aircraft. And what we have seen, and generally smaller airports will have a shorter minimum connecting time, while larger airports will have a higher connecting time because you have to walk more and etc. On the other hand, you have maximum connecting time. So this is the maximum time that passengers are willing to wait when making the transfer. So passengers will not be very happy if they have to wait for 3 hours for the next flight. So there is a certain maximum limit also. So it could be it could vary from 1.5 hours to 2 hours. Apart from that, you have detour time. So detour time is the ratio between the sum of flight distance of flights I and J to the distance between the the distance between the origin and destination, if there's for a direct flight, in terms of distance. And this ratio should not ideally be more than 1.4, meaning the passenger should not be traveling on a very long route to reach his final destination. Okay, now this is a long paragraph, but I'll explain the meaning of this. So what it means is we will try to minimize the total weighted flight slot displacements, meaning we should try to minimize the number of deviations, the amount of deviation in time of the original flight and the new and the flight according to the new schedule as per the model. And when we are doing the displacement, we should be ensuring that we try to, if it's a more critical flight, meaning it's a flight to a bigger airport, then we should be trying to reduce the deviation, while if it's a flight to a smaller destination, then we can have more deviation. So these are some of the constraints which need to be adhered to. So basically, it is all in terms of connecting, the arrival flight and the departure flight. These are all kind of mass balance constraints, as we saw in the earlier class. But this constraint is important. That means there is a limit on the maximum displacement of any single flight, and all the displacements are expressed in terms of 15-minute periods. And also in a particular slot, in a particular 15-minute slot, we cannot assign too many. So there's a limit on the number of flights you can assign in a 15-minute period, because the airport will also have a certain capacity in terms of the gates, boarding gates. So we cannot assign more flights than that limit. Okay. So any questions on this? Okay. Okay. So now I'll go to the next problem, which is the aircraft landing problem. So what happens is, you might have seen that sometimes when the runway is very busy, the aircraft takes a long time to land, and similarly, while during the process of landing, sometimes the aircraft takes a bit longer than anticipated. So how and this happens. This is more common in the more congested airports. For example, in Delhi and Mumbai airport, this would be a very common scenario, because the runway capacity is overutilized. So what we try to do in this problem is, we have a certain number of aircrafts landing in quick succession at a particular airport, at a particular at the runway, at the airport runway, and we need to assign what should be the optimal landing sequence of these flights. So that's what we try to solve in this problem, and we look at different aspects of safety, efficiency, and fairness in the process. So what happens is, once an aircraft starts descending, maybe like 30 minutes before, and again depends on whether it's once an aircraft starts descending, maybe 30 minutes before the landing time, it can accelerate or decelerate based on how fast it gets access to the runway. So the air traffic controller will let the flight know what is the landing sequence, and accordingly they will land. Accordingly they will accelerate or decelerate, and then they can land. So what are the objectives here? So from the airlines perspective, the objective would be to obviously to make sure that I land before all other aircrafts, because then the passengers delay is reduced, and the fuel cost is also minimized. While for the air traffic controller, they need to ensure that all the aircrafts uh, we are assigning a fair scheduled for all the airlines, for all the aircrafts, all the flights, and the runway throughput is maximized and their workload is minimized. So what are some of the constraints? So after having reached the radar range of an aircraft, airport aircraft can accelerate and decelerate. This is already discussed. And we assume here that there is no go around. That means the aircraft can either accelerate or decelerate, but it will eventually land, and it doesn't need to go back. So the only thing is, it has a certain upper and lower bound on the time within which it can land safely. The other important constraint is separation requirements. So because whenever an aircraft lands, there is behind the aircraft there would be a lot of turbulence in the air. So that would affect the next aircraft which is on the runway. So there is some minimum separation which has been mandated by the International Civil Aviation Organization. So this minimum separation is influenced by two factors. One is the weight of the preceding aircraft, and the second is the weight of the trailing aircraft. So you can see the minimum separation distance between each combination of aircrafts. Each combination of preceding and following aircraft. So if the following aircraft is light, then it would have the minimum separation distance would increase, while if it is heavy, it would decrease. So if you see in this table, if the preceding aircraft is heavy and the following aircraft is heavy, the minimum distance requirement is just 96 meters, while if it is the following aircraft is light, it increases to 196 meters. The third important constraint here is constraint position shifting, which means this puts a limit on the maximum possible deviation from first come first serve. So that means if I have so if the maximum deviation allowed is 4, and if I have aircrafts 2 to 7 waiting for landing, then aircraft 2 has to land before 7 because the gap is more than 4. But it can land before, it can be overtaken by aircrafts 3, 4, and 5, and 6. Okay. Any question? Okay, so this is a sample output of what the output would, sample output of what the runway allocation would look like. So this shows in this picture you have two runways, A and B, or you can alternately call them as runway 1 and 2. And it shows the allocation of aircrafts between to the runways between 7 a.m. and 8 a.m. approx. And you see different colors here. So the green numbers, the green alphabets represent whether the aircraft was high, low, or heavy, light, or medium. The blue, the numbers in blue represent the aircraft number, and then you have the orange and white colors in the chart. So the orange colors represent the minimum separation time, and the white colors represent the runway idle time. So only the white sections represent the idle time. So if you see here, there are some areas where there are some cases where the runway idle time is 0. For example, if you see here between 16 and 14, there is no white area. All right. So if you look at this this picture, you will see that for example, aircraft after aircraft 8 we have aircraft 6, and not the opposite way. So so aircraft number 6 lands after aircraft number 8. Okay. Any questions on this use case? Okay. Now the other important aspect is we have a lot of ground handling vehicles in the airport. So how do we ensure that their schedules are coordinated and optimized so that the aircraft can depart on time? So okay, can anyone tell me what are the different kinds of ground handling vehicles that are there in an aircraft in an airport? Anyone? Are you guys able to hear me? Anyone can tell me what are some of the ground handling vehicles? Okay, so one is the vehicles or the buses which will carry the passengers from the aircraft to the terminal, or vice versa. The second is you have the fueling vehicles. Fueling vehicles to refill fuel after the aircraft has landed, or you can. And the third category is are the vehicles which carry the baggage of the passengers. So let's look at how the sequence looks like. So one rule here is that the refueling can happen only after, for a flight which has landed, it can happen only after the passengers have disembarked, and it has to get completed before the passengers boarding. Meaning, in simple words, the refueling has to happen while the aircraft is empty. So these are the sequences I think which all of you are aware of. But what it shows here is that after the aircraft lands and arrives at the stand, then the passengers start disembarking, and as soon as the aircraft arrives, the passenger bus also starts for its starts so that it can reach the aircraft by the time the aircraft arrives at the stand. And then as the disembarking happens, during the process of passenger embarkation, the refueler also starts arriving at the stand, so that by the time the disembarkation is complete, the refueler service has started. And as soon as the refueler service is over, the passengers who will be departing on the same aircraft to the next destination, they will be arriving at the aircraft, and once they board, the aircraft takes off. So this is a sequence of operations. So what are some of the objectives that we need to satisfy in this problem? One is obviously the ground handling vehicles are limited in number, so we need to ensure that we are minimizing their usage, because one is obviously the cost will be lower if we use less vehicles. The second aspect is, since the space is limited in the airport, it will help to reduce the utilization of space also. And the second objective is that the ground handling service vehicles should complete their tasks as soon as possible. And the third objective is the workload of these vehicles should be distributed as much as possible. So these are some of the objectives, and again, this picture here is just showing the sequence of operations what we already saw. So the objective is we should not be wasting time for the aircraft should not be wasting time waiting for the ferry service to arrive, or waiting for the refueling service to start. So the refueling service or the ferry service should be in time, should have reached the aircraft in time. And they should be leaving that aircraft in time, so that it can reach the next aircraft for refueling or for ferrying the passengers in time. So these are some of the constraints that the ground handling vehicle starts from and returns to the depot. Meaning, if it's a passenger bus, it should start from the terminal and return to the terminal. Yeah, and these are some restrictions in terms of the time windows. Yeah, I think most of these we have discussed. Okay. The other aspect is aircraft maintenance, scheduling, and reassignment. So there can be different types of aircraft maintenance. So aircraft one is type A check, which happens once every. Okay, before I go to the details of types of maintenance. So what happens in airlines is they need to undergo maintenance at a certain at a certain frequency, and when they go for maintenance, obviously for that during the period of maintenance, they cannot operate any flights. So those flights we cannot obviously cancel those flights. Those flights should be assigned, or rather reassigned, to another aircraft. So how we do that reassignment, that is which aircraft should be assigned to those flights, that is what the model does. So what happens is there are three types of maintenance requirements in any aircraft. One, the most frequent type of maintenance is type A check, which happens once every 65 flight hours. So let's say once every week, where all the major systems are checked. And the second type is type B check, which happens once every 300 to 600 flight hours. So let's say once in every 1 or 2 months. Third is type C and D checks, which happens once in every 1 to 4 years. And this requires around 1 month of a time. But we do not consider type C and type D check because they are they are pretty infrequent, and so we consider only type A and B. So what we need to minimize here is the total cost of type A and B maintenance check. Now, this type A and B again requires a certain different duration. So I don't know what is the duration, but during that duration, they cannot operate any flight, and this maintenance happens at any of the airports. So what they will do is whichever is the last destination, that needs to be decided in such a way that the maintenance would happen there. Okay, and coming to the constraints, there's a certain limitation on the number of. Now, all the airports do not have a maintenance base. Only some airports have a maintenance base, and there is certain limitation on the number of aircrafts that can be served at a maintenance base on any particular day. And this capacity depends on the number of available mechanics and the available inventory of various aircraft parts. So obviously we can assign a particular aircraft for maintenance check at a city on a particular day only if it is available at that city on that day. So type A maintenance check happens once in 4 days, and type B maintenance check happens once in 2 months. Yeah, I think these are and the assumptions are there is these maintenance bases located at the airport. There is no aircraft, so aircraft do not operate during the night, and these maintenance checks are performed only during the night. And the model would suggest. Apart from suggesting the flight which needs to be reassigned, it also would suggest where the maintenance should happen. So it would suggest only one of the existing maintenance bases, and it does not recommend any setting up any new maintenance base. And we also do not model unexpected maintenance requirements. In terms of objectives, another important objective here is that we will be trying to assign an aircraft of that type, of a suitable type, meaning if we assign an aircraft which is much smaller in size, that would lead to revenue loss. While if we assign a much bigger aircraft, then it would be an additional cost, because a smaller aircraft could have sufficed the demand for that origin and destination pair. Okay. I think this one will skip. Okay. Any questions on this slide on the airlines use cases? Okay. Okay. So I think this one also we can quickly cover. So what we do in this model is we try to decide how many between a particular origin and destination city, how many aircrafts we should operate, and of what type, based looking at the price offered by the competitor airlines and the demand that I have on that sector. I would take these decisions. The concept here being that again, if we assign a bigger aircraft, then it would lead to an additional cost, while if we assign a smaller aircraft, I might lose revenue. So what are some of the constraints that we look at here? That on a particular route, we cannot exceed a maximum flight frequency, and also any airlines would have limited number of pilots, and the pilots also have a limitation on the number of hours they can fly every month. So that also needs to be taken into account. We also need to look at the maximum captured passenger demand on each route. So obviously, if we operate too many flights on a route than required, then there'll be less sell, because we don't have that many. There'll be some unsold inventory because we will not have that many people to buy tickets. Yeah, I think these are the constraints. Okay. Okay. So any questions on these slides? Why everyone is so silent today? I hope all of you are able to hear me. My audio is clear.
Yes, sir.
Okay. Okay. So now I'll move to another topic, which is optimization solvers. So I think this is something we have not covered so far. You can see the okay. So we'll try to go through some of these points. So one is we look at what are the commercial solvers commonly used, why we cannot use open source solvers in optimization, and okay, so this one we'll probably not go through today, and okay, so these are some of the popular optimization solvers. um, so rather commercial optimization solver. So the gold standard in optimization is IBM iLog Cplex. So it's or in short you can call it Cplex also, or iLog Cplex also. So Cplex was originally belonged to a company called iLog. Then IBM purchased iLog I think in 2008, and since then it is called IBM iLog Cplex. So this is the gold standard in optimization and is also most expensive. So each license of this solver costs around $60K, which is around 30 lakh rupees. The second most popular solver globally is Gurobi. This is much cheaper. Comes around one-fourth the cost of Cplex. And again, these costs are not standalone cost, meaning it's not just one size fits all cost. So these costs depend on multiple factors like whether you need a developer license, whether you need a server license, a floating license, or a license for nonlinear programming, or only for mixed integer programming. So those kind of things, multiple factors are considered here. And apart from that, we also have FICO Express, which is again much cheaper than Groby. Apart from this, there are some lot of other commercial solvers. For example, SAS also has its own commercial solver, which is called SAS OR. Okay. Now, in terms of modeling languages, so these commercial solvers can be integrated with any standard programming language, and they have their own API where you can write the model, or you can invoke these solvers from different any programming language like Python, C++, C Sharp, Java, whatever you want. Okay. So apart from this, now coming to open source stuff, we have certain modeling languages which are not like standard programming languages, but they are more, you write the uh, model, you write the code in the same way as you would write a mathematical model. So for to write in these languages, you don't really need to know any programming language. If you are able to write in the optimization, if you are able to write the optimization formulation, you can write the model in these languages also. So they have their own syntax and commands. So they have again free. Some of them have free trial versions, free license for academia, etc. So some of these languages are AMPL, GAMS, and OPL. So AMPL stands for a mathematical programming language. GAM stands for General Algebraic Modeling System. OPL, I don't remember. Apart from that, Python has its packages for optimization like Pulp and Pyomo. Julia has this package called Jump, JUMP, and MATLAB also has YALMIP. So these are all obviously open source. Apart from that, you have Google also has come up with Google War Tools, which is open source. And even in Excel, you can solve problems up to a certain size limitation. So these open source solvers have limitations in terms of problem size they can handle. And typically, smaller companies or startups who do not want to invest too much in commercial solvers, or they do not have problems which are that big or complex, they sometimes go for open source solvers. So why, another question obviously comes is why we have so many, why we do not have open source solvers in OR unlike MLAI. So in MLAI, I think most of you would be using Python. Apart from that, we also have R, etc. But why we do not have, why that is lacking in OR? So these are some certain reasons. So one is probably the most important reason is dearth of technical talent, meaning dearth of people who can write solvers, create solvers. So number of people who study ML is many times more than number of people who study OR and who can write solvers. So that is the primary reason. Also, there is a lot of corporate money which goes into the development of solvers. I mean ML frameworks like Python and R, which is missing in the case of OR. And the simple reason for that is the number of people using OR is many times less the number of people using machine learning. So that's why we don't have much development in the optimization space in terms of open source solvers yet. Okay, now coming to the differences between open source or other limitations of open source solvers when with respect to commercial solvers. So commercial solvers are sometimes more than 1,000 times faster than open source, and they are very robust. So if you use if you use an open source solver for a long time, you will find a lot of bugs, while commercial solvers go through a thorough process of Q&A, and they have hundreds of developers, and they get a lot of feedback from customers. So they have fixed all those issues. That's why they are much more robust. Now, and the other reason is in solver companies, commercial solvers spend a lot of money and time to build and test good interfaces so that they can be called from any programming language, any GUI, any modeling framework. While in open source, there is little, obviously there's little incentive to do that. So that is why it is much more, commercial solvers are much more easier to integrate with any kind of framework that you can think of. Better user experience. Yeah, I think this is very obvious. Support or technical support. So if for commercial solvers, if you are stuck on any problem, you can always reach out to the solver support team, and they will be happy to help you. Not just because you have paid them money, but because the more problems you give them, those problems, those real life problems, they can test on, and they can they can find out some issues using your problem, find out some issues in their solver using their problem, and that will help them to improve their solver further. Performance tuning, again, they get the commercial solver teams get a lot of real life problems from customers, so they can very easily tune the performance or improve the performance. Data bandwidth. So what we have seen so far is optimization problems sometimes deal with humongous amount of data. So with commercial solvers, it is much easier to process that volume of data, which is not possible to do with open source solvers. So what makes a solver robust? It should be able to solve an MIP to optimality. It should be, so in the last class we saw how to detect infeasibility using IIS. So it should be able to detect infeasibility in the model fast and report and find out the reason for infeasibility. If the model is feasible, then it should be able to find the feasible solution quickly. And sometimes we need multiple solutions, so it should be able to find all the multiple solutions and store them. Apart from that, it should also be able to recognize, not all MIPs are same, so the structure of an MIP would differ a lot between problems. So it should be able to recognize the problem structure and adjust the solver parameters or strategies accordingly. So we'll look at what is solver parameters later on. And they can deal with both with small and very large scale problems with equal ease. And if there is a numerically difficult instance, then it should be able to handle that efficiently. So these are some of the features which determines how robust a solver is. Okay, this one will go to the next class. So these are, so before I come here, actually, let me go to this one. So these are some of the termination parameters in most frequently used termination parameters in optimization solvers. So if your model takes a lot of time and you don't want to wait for that long, then you can put a certain time limit on what is maximum time you would want the model to solve. So if the model solves in less time than the time limit, then it's good enough. It's good. And if it takes more time than this time limit, then you stop at the time limit. You do not want to. You do not let the model stretch beyond this time limit. So if you look at this log, you will see that. Okay, we'll go through the log in the next class, but here it says that maximum time limit reached, maximum time is 10, and we have already taken 36 seconds because it was going through. Anyone can tell me why it stopped at 36 instead of 10? Okay, so it was in the middle of processing a particular node, and it didn't want to. It didn't interrupt while that node, because the node wasn't complete. But once that node was completed, then it stopped because it has crossed the time limit of 10 seconds. So that is one way in which you can terminate a solve. The other way you can terminate a solve is by putting an optimality gap. So optimality gap is basically the deviation from the difference between the best known solution, that is what we have got so far, and what is the best possible solution. So in this screenshot, what you see is that the optimality gap decreases gradually from 100%, but it is stuck at 0.22% for some time, and then it reaches 0.01% at around 3 minutes. So generally, this is highly non-linear. So as you reach closer to the optimality gap, the time taken to reach that gap increases exponentially. So as you see here, it reaches 0.22% in 74 seconds, but to reach 0.01, it takes another 100 seconds. So generally we put.
So how do you calculate this gap? Because for this, don't you have to know what is the optimal solution?
Yes. Yeah. So I'll come to that. So I haven't put that in this slide. I'll put that in the next slide. So basically, it uses some machine learning algorithm to estimate what will be the best bound, and this best bound will reduce, meaning for a minimization problem, this best bound will increase as you progress in the solution, and the best bound is what is the best possible solution, and the solution that you are getting the best known solution, that value will keep reducing. So what the optimization model will try to do is it will try to reduce the gap between those two values. So it estimates. So the answer to your question is it will estimate the best possible solution by it uses some machine learning algorithm to find because it knows what are the nodes it needs to further branch on, and how far it is, how many nodes are still unexplored. Based on that, it will estimate that. Okay. Did that answer your question?
So using this machine learning model, what we estimate?
We estimate the best bound. That is, we estimate the best possible solution that we can get for for my problem.
So machine learning model also giving you a solution. Is it?
No, it is not. It will not give me the solution. It will tell me what is the best possible solution. But that I mean, you can, that will give me the best possible solution of the objective function, best possible value of the objective function. But how do you change the variable values to get that, to reach that best possible solution? That has to be determined by the optimization model.
Okay.
Yeah, but that's a great question. Yeah, that is a very commonly asked. I mean, that is a question which people ask sometimes. Okay. Any other question? So in in real life problems where you need solutions in 2-3 minutes, like airlines rescheduling, those kind of problems, generally even a 5% optimals, meaning a 95 0 point sorry 5% optimal solution is also good enough. So if that means you're 95% close to the best bound, that is also good enough. Okay, now here we'll go through some tolerance values. So we have in computer precision there are different tolerances. So in optimization also we have certain tolerances. So the first first tolerance that we'll go through is integrality tolerance. So integrality tolerance is how far is what is the tolerance of on the integral um on the integrality of integer variables, meaning if I've defined a variable as either integer or binary, then how far can the model output be different from that? So let's say if in this case in this example I can get the value of a certain decision variable. Let's say x is my decision variable, which is binary, and instead of giving me a value of 1, the optimizer gives me a value of 1 point 6 zeros and then 465. But this is not wrong, because this is less than the integrality tolerance, which is 1.1, which is e to the power minus 5. So anything which is lower than the tolerance, any value where the deviation from the integral nearest integer is less than the integrality tolerance, is okay. Similarly, if we have feasibility tolerance, so and by the way, because of this integrality tolerance, sometimes instead of let's say decision variable's value is let's say it's a binary variable, so it should be either 0 or 1. Instead of 0, you can get minus 0.000001. So that's not wrong, because although it is negative, it's actually 0, because since it is less than the deviation is less than the integrality tolerance, we can consider that as 0. Similarly, we have feasibility tolerance. So feasibility.
So we specify this, right, that this variable is binary to the model.
Mhm.
Then why it does give like this kind of values?
Yeah, so it gives because we have a certain tolerance limit, and we can deviate within the tolerance limit. So the reason is because if we make, now you may ask why it is not exactly 0, because if we make it exactly 0, it will be much harder for the optimizer to make something exactly 0. So it might take much more time. So that is why we make it exactly I mean, we have this tolerance values. And okay, in your problem maybe even this point 0.0000465 is also non-negotiable. I mean, it's also on the higher side. So let's say you're in the you are in an industry where there is absolutely no scope for any deviation. So then you can specify an even smaller value, like let's say 10 to the power minus 9 or 12 or whatever. But then that will make the solution, that might make your solve slower, because then the optimizer has even less tolerance on how much it can change the values of the variables. Okay.
Okay, sir.
Okay, so now so this default of 10 to the power minus 5 is generally the default for most solvers. Now feasibility tolerance, and again these tolerance values, these are not, some of the concepts that we will go through here is not specific to any solver. Most of the solvers use similar concepts. The next thing is feasibility tolerance. Feasibility tolerance is how much my constraint can, the RHS of my constraint can violate. So meaning, let's say I have a constraint x plus y is equal to 10, and you might get the optimizer can give the value of x as 6 and y as 4.000001. So again, it is not, x plus y in this case will not be exactly equal to 10, it will be slightly more than 10, but since it is within the feasibility tolerance limit, I am okay with it. I mean, that's okay. So again, for this, the default value is 10 to the power minus 6. And you can have similar tolerance on the on bounds of a variable also. Now, what happens if you increase or decrease these tolerance values? So if you increase the tolerance, the magnitude of the violation will increase, but obviously that will reduce the chance of infeasibility, and the solve time may decrease. While if you decrease the tolerance values, if you decrease the tolerance values, magnitude of violation will decrease, and your chance of infeasibility increases, and the solve time may increase. Okay. Now, what is optimal tolerance? Now, in simplex method, you have seen that we move from one corner point to another corner point of the feasible solution space. If there is an improvement in the objective function, and when we see that there is no further improvement, we stop at that corner point. So now, to move from one corner point to another corner point, we need to check if the objective function value increases. Now, if the change in the objective function value is less than this optimality tolerance, then we do not move. So we move to another corner point only if the delta is greater, delta in the objective function value at the two corner points, at the new corner point is beyond this optimality tolerance value. Markowitz tolerance is again another tolerance value. You can read about this. So this will range between 0 to 1, and its default value is 0.01. But sometimes if you increase this to, let's say, 0.5, it helps to solve the problem faster, but not always. So larger values reduce the error introduced in simplex basis factorization. And it may avoid numerical problems in certain rare situations. Okay, so what else? I'll go through this in the next slide, next lecture, but quickly we can complete a few more things. So before we go to the main, the mathematical solution of the problem, before the solver starts solving the problem, it does something called pre-solve. So pre-solve is essentially simplifying the problem by detecting and removing redundant constraints, tightening variable bounds, etc. So let's look at this. So let's say if it's a simple example is, let's say if you have two constraints, x less than equal to 2 and x less than equal to 3, then it can drop the constraint x less than equal to 3 because x less than equal to 2 will satisfy both. So another example that you can see here is this, what I put in this picture. If you focus on this, these 5 constraints, rather this 4 constraints in this objective function. So so if you see this one, since we are maximizing x minus x3, that means we are minimizing x3. So x3 can be reduced to 0, and if x3 is reduced to 0, that means we can drop constraint 3, because then x1 plus x2 plus x4 greater than equal to -1, which is basically, and anyways all of them have to be greater than equal to 0, so that constraint is redundant. So constraint 3 can be removed. So this is another example of pre-solve. So if you look at this, so this screenshot in black, what I put, this is from the solver log. So what it says here is, so rows and, so what are rows? Anyone can tell me?
Constants,
Yeah, and columns.
columns are variables.
Yeah, and okay, so other things I'm going to describe. So elements, I forgot what it is, but globals is number of number of integers. So if you see this one, the original problem has around 24,000 constraints, 30,000 variables, and 30,000 integers. So this, so after pre-solving, this got reduced to 7,000 constraints, 12,000 variables, and 12,000 integers. So and it says that pre-solve finished in 0 seconds. So in 0 second, it was able to simplify the problem by around, it was able to reduce the problem size by around about 60-70%, right? And for this problem, I mean, I picked this example from somewhere in the internet, but if you had not, so let's say if you do not want to go for pre-solve, that is, if there's a feature where you can turn off pre-solve. So if you turn off pre-solve, this problem would have taken 30 minutes. But because you are pre-solving the problem, meaning you are removing all the redundant constraints, etc., the runtime gets reduced to 25 seconds. So this is one example of this is how pre-solve works. And in some cases, in pre-solve can also help to find at pre-solve stage itself, the model can the solver can detect infeasibility, or you can find optimal solution. So sometimes it might happen that your problem is so trivial that the pre-solved problem has zero zero problem size. So that means without solving the actual problem, you can find the optimal solution at the pre-solve stage itself. And these are some constraints. I'm sorry, these are some features. So if the pre-solved model is infeasible, then the original model is also infeasible. Similarly, if the pre-solved model is unbounded, the original model is also unbounded. That's it. And these are the different types of pre-solve reductions which the solvers can do. So I'll not go through this, and even I don't know everything about this, but to summarize, it can reduce individual constraints, it can reduce individual variables, it can consider multiple constraints at the same time and reduce them, it can consider multiple variables at the same time and reduce, and there are reductions that can consider the whole problem. So these are the different kinds of pre-solve reductions that solvers are capable of. So this is a very powerful feature which a solver has. So sometimes I think in the previous classes I asked you questions on if you have this extra constraint, if this additional constraint, then does it reduce runtime or increase runtime? So this is the answer. So even if you have have any redundant constraint, you don't need to worry. Because the pre-solve problem will, the pre-solve will drop that constraint. Okay. So I think we'll stop here. Any questions? Okay. I think if not, then we'll again meet online on Thursday, 27th at 3:30. In that class, we'll discuss I'll show you the demo solution of the first assignment. Okay. Okay then. Thanks everyone. Have a great evening.
Thank you, sir.